Okay, so let's talk about characterizing a set of measurements using numerical methods. Graphical methods are useful to visualize a data set, but it's often better to have a numerical description. We focus on two concepts here, the measures of central tendency and measures of dispersion. Now, there are different terminology that's used here sometimes. Sometimes you just say measures of center, instead of saying dispersion, sometimes we say measures of variation or measures of spread. But what we're talking about here is where's the center of our data set? That's our measures of central tendency. And how spread out is that data set? That's when we're dealing with measures of dispersion. I think it's important to remember here the big picture. The big picture is that we are thinking about a population that we really don't have our hands on that population. It's really, this big conceptual group. And we're just trying to make some predictions about that. But what we only have to look at is the sample. So I like to think about this sometimes as like a fried egg. Let me just draw this out. Let's see if we've got like a fried egg here. And we've got the yolk here in the middle. And so what we've got out here is we've got the population. And remember, that's the big group that we don't really have, we can't get our hands around that whole thing. What we can do, though, is we can look at a sample. And so what we're doing here is we're thinking about things in here. We're looking at what's in here, and we're trying to make predictions about the entire thing that's going on out here. And so we're going to look at some different measures of numerical measures that will be coming from the sample. But what we're hoping to do is use those to predict what's going on here with the population. So the first one is the arithmetic mean. It's the most often used measure of central tendency. It's commonly referred to as just the mean, though there are other types of means, the geometric mean, the weighted mean, etc. The goal of statistics is to estimate the population mean, mu, which we generally do not know, with the sample mean, y bar. So if we go back and think about this, out here, mu is the thing that we really generally don't know, but we're going to be able to find, the sample in here, and we're going to call that y bar. Now, some textbooks will write this as x bar. Generally, when you have a bar on top of this, when you're dealing with statistics, you're talking about some kind of a mean. So the sample mean of a set of n measurements is denoted by y1, y2, all the way up to yn, is y bar equals 1 over n times the summation of y sub I, where I goes from 1 to n. So think about what this is doing. All we're really doing here is we're just saying that y bar is equal to 1 over n times the summation of the y sub i's. The y sub i's, these are just the data elements here. I goes from 1 to n. And if you think about this, all that right there is doing is summing up all your data values, and then we're dividing by n here, since n is in the denominator. So we're just adding everything up, and we're dividing by how many we got, which is the standard way that you would calculate an average. So it's important to note that the mean of a data set only locates the center. By itself, it doesn't provide an adequate description of a set of measurements. It's possible for two sets to have the same mean, but wildly different frequency distributions. An adequate description of a set of data requires that we define measures of the variability of the data. That is, the variability is the spread of that data. The most common measure of dispersion, or spread, is the variance, which is the average of the distances of the measurements from the mean. So here we have the formula for the sample variance. Okay, so let me click over and write that down. Sample variance, S squared is equal to 1 over n, and just make sure I'm copying this exactly the right way. Okay, so 1 over n minus 1 times, 1 minus n minus 1 times the summation as I goes from 1 to n. And what we have here is we have y sub I minus y bar squared. Okay, so let's think about this formula for just a moment. What this is doing is this is actually giving us some kind of an idea about, it's sort of working as a prediction of the population variance. Now I'm going to write down the population variance. If I have the entire population, then the population variance would look like this. 1 over n times the summation, I goes from 1 to n, of y sub I minus mu squared. Now, this would be the population variance. And I'm only showing you this because I think it's a little bit easier to think of it in terms of this, and then we'll come back and kind of think about this formula up here for a moment. Now, think about what this is. So we have our data values, right? That's y sub I. That's each data value. And from each one, we're going to subtract off the mean. So that's the difference between the data value and the mean. And then we square each one of those things. Okay, so what we have is we have a set of numbers that are the squared differences from each data value to the mean. And then we add all of those up and divide by how many we got. And when you're adding everything up and dividing by how many you've got, you're just finding an average. So if we have the population that we're looking at, if we have all those values from the population, then we know that what the variance here is giving us is giving us the average squared difference of all the data values from the mean. But as we were saying before, usually this we don't know. We usually don't know the population. Usually the only thing we have to look at is the sample. So let's assume we don't know this. Then let's go up here and think about this one then. So what we have in this case is, well, pretty much the same thing. We start with the data values. We subtract the mean of those data values. So that's going to be the distance between each data value and the sample mean. We square each one of those things, and we add them all up. And if we were to divide by n here, then this would pretty much be exactly the same thing we were doing with the population variance. But we're not. We're actually dividing by n minus 1. And so what's happening is that when you have a sample variance, this is actually a modified average. It's not exactly an average. It's a modified average of the squared differences. The one reason why we divide by something a little bit less than n is because on average, the spread that's in the sample is going to be no more than the spread that's in the population. Think about it. If you've got a population that's got a certain amount of spread in it, and then you take a sample from that population, you're probably going to miss out on some of the, some of the data values in there that cause some of that spread. And so we know that on average, the sample variance underestimates the population variance. And that's why we're dividing by something a little bit less right here in the denominator, because that's sort of making up for that. It's making this a better prediction for the population variance. Okay, so we've got a formula for this, and it's not that tough to go in here and do this. Usually, though, we use technology to find these things, and so I'm going to show you that here in just a bit. So as before, we can also discuss the variance of the population if it's practical. In that case, the population variance is denoted by sigma squared, but again, we usually don't know that. Now, another measure of variation is the standard deviation, which is simply the positive square root of the variance. The sample standard deviation of a data set of n measurements, denoted by y1, y2, up through yn, is s equals the square root of s squared. So all we're doing is we're taking the square root of that variance, that sample variance that we found before. You may wonder, why do we do that? Why would we go back to the square root here? The reason is that when we look back at that population variance formula, we see that we are squaring these distances here, right? The data value to the mean, we're squaring those distances. So if you think about a data set that involves something like, I don't know, say it involves temperatures. So its measurements are in degrees. When we go in here to find this variance, we're going to end up with degrees squared, which doesn't make a lot of sense. Squared units usually don't mean very much. So does degrees squared, hours squared, miles squared, those things don't mean very much. So what we do is we take the square root, and that gives us a standard deviation. It gives us another measure here, but more importantly, it brings our units back into something that we can understand. If you have degrees squared and you take the square root, now you just have degrees. So you have a measure of spread that is in the same unit as the data set itself. And the corresponding population parameter is the population standard deviation, sigma, which is the square root of sigma squared, that population variance that we had. But again, we generally don't know that. So many distributions of data in real life have bell-shaped relative frequency distributions. Many of them have this shape that sort of is unimodal here in the middle and symmetric out here on the ends, and so this shape is generally something like a bell. Now we're going to see this type of distribution a good bit later on in this course, but for these distributions there's a special property called the empirical rule. So when we know that our data set has a bell shape to it, then we're going to think about this thing called the empirical rule. Now we actually call these things normally distributed. A normal distribution means that there's sort of a single mode here in the middle, a highest point here in the middle, and it tapers off on both sides in a symmetric way. So when a data set has a bell-shaped histogram, or a normal distribution, it is often possible to use the mean and standard deviation to provide an approximate description of the data using a rule known as the empirical rule, which says this: approximately 68% of the data will be within one standard deviation of the mean. Approximately 95% of the data will be within two standard deviations of the mean. And all or almost all of the data will be within three standard deviations of the mean. Now what we mean here by one standard deviation of the mean is that whatever the mean is, you subtract one standard deviation from that and add one standard deviation to that, and you get an interval. And that's in that interval, about 68% of the data will be there. So here's a graphical look at that. We have X bar in the middle, subtract and add one standard deviation, and about 68% of the data is there. Subtract and add two standard deviations, about 95% of the data will be there. And subtract, three standard deviations or add three standard deviations, and you've pretty much got the whole data set. So let's look at an example here. So I'm going to show you a table that presents body temperatures for a sample of 40 people. We're going to use Excel to find the mean, that's going to be our measure of central tendency, the variance, that's a measure of our spread, and the standard deviation, which is another measure of spread, but it has the same units as the data set. We're going to round these to 2 decimal places. We want to determine the intervals used in the empirical rule to find the frequency and relative frequency of observations that lie within each interval. All right, so we're going to think about what's within one standard deviation, what's within 2 standard deviations, and what's within 3 standard deviations. And we want to see, do those percentages agree with the empirical rule? Okay, so here are my body temperatures. And what I'm going to do is I'm going to go over and I'm going to copy these things into Excel. I'm going to pause the video for just a moment and copy these things over, and then we'll take a look at how to do all of this. Okay, so I've copied all of my data here over into Excel. And I've just put it into a single column here instead of having it in a table like it was in the other application. And what I want to do is I want to find the mean, the variance, the standard deviation, and I want to think here about the empirical rule and those different intervals that I'm going to get. Okay, so I'll show you some tricks that I know here in Excel that may make this go a little bit easier. I'm going to select all of my data right here. Okay, so I'm going to select this entire column of data, or all of my numbers here. I'm going to just put my cursor here on the top one. I'm pressing Shift on my keyboard, and I'm pressing Control, and I'm pressing the down arrow key. And then what that has done is that has selected all of my data. Now you could have done that just by selecting this and dragging it and using the cursor. But the shift, control, and down arrow key select all of those things in a pretty easy way. I'm going to go here to the name box. Right now it's got a just a location of the first data cell here. I'm going to go into the name box and I'm going to name this data set. Now these were emissions, so I'm going to call this EMISSIONS, emissions. Okay, so I'm going to press enter. And now in Excel, every time I type in emissions, it knows I'm dealing with this set of data over here. So we were asked to do some different things here. We were asked to do the mean. Okay, and remember this is actually, this was a sample, so we're actually doing the sample mean here. In Excel, the sample mean, or the population mean if you have the population to work with, it's those are calculated the same way, and that's really just an average. So I'm going to type equals, and the command to use here is average. And now it's looking for the data. What do you want an average of? And I want it to do the average of all those emissions. Remember, emissions, I've defined that to be my data set over there. When I press enter, it gives me my emissions. Okay. I want my variance. And again, remember this is the sample variance. So I'm going to type equals VAR. That's the command for variance. But there's actually more than one here. You have var.p, which means that if you have the entire population that you're looking at, if you have a set of data here that represents the entire population, then you would use that one. But we have the sample, so I want var.s. That calculates the sample variation. And remember, the formulas we were looking at just a little while ago, those things are calculated differently, so it's important to choose the correct command here. So I want the variance of the emissions. And I get a number here. Honestly, that number doesn't mean a whole lot to me, because remember, though that has squared units. That's like the temperature squared, like the degrees squared or the hours squared. I don't really know what the variance means, but it is a measure of spread. And if I had one data set and I had the variance of it, and I had another data set and the variance of it, I could look at those two numbers and see which one is the higher number, and I could tell from there which data set is more spread out. So you do get some information, but not a whole lot. Okay, so I want the standard deviation. Now, I could do this in one of two ways. I could say, okay, equals square root, that's SQRT, of the variance. And it gives it to me that way. Or I could go in here and I could type in equals STDEV. And again, if I had the population, I would do .p here. But I'm dealing with a sample, so I'm doing .s. And I want the standard deviation of the emissions. Okay, I guess I need to spell it correct. There we go. Okay, I'm going to go up here and I want to, let's see. Okay, give me a moment. Okay, so what I'm trying to do is I'm trying to just bring these down to 2 decimal places. I'm going to go to the number here and just go in and decrease until I get down to, well, it's covering up. I can't tell. No, I went too far. 2 decimal places. Okay, so we've got our mean, our variance, and our standard deviation. I wanted to think about those intervals that come from the empirical rule. So that is, I need to find the mean minus 1 times s and plus 1 times s. That's going to give me the interval that's within 1 standard deviation of the mean. And do the same thing with 2 times the standard deviation. And do the same thing with 3 times the standard deviation. Okay, so I could just calculate those things, you know, using a calculator or just however I want to here. I'm going to do this a little bit differently. I'm going to call this K. So K represents the number of standard deviations away from the mean. And so I'm doing this for 1, 2, and 3. Okay. Now let's see here. I want to center this. Okay. So here I'm going to do the lower interval, or the lower number of that interval, and upper number of that interval. And so what I've got here is I've got equals. The lower number would be the mean minus K, which in this case is going to be 1, times the standard deviation. So I want to do the mean. I go up here and I select the cell where the mean is. But I'm going to be copying this cell, you know, down into different places. I'm going to be copying this formula. And I don't want that mean, that reference up to that mean to move. So what I need to do is I need to put in what's called an absolute reference here. And this absolute reference means that when I copy this formula into different cells, the place it's looking back to isn't going to change. I don't want it to copy that reference. Now you can do this just by pressing F4. You see what that does is that puts dollar signs in front of the D and the 2. And those dollar signs are your absolute references there. And what that means now is, okay, I'm going to just, you know, I will always look back at D2 in this formula. And remember, that's your mean. And I want that to be this minus K, which in this case is 1. Okay. And I don't really want this I don't want this to be absolute reference because I want it to copy this. I want it to be, you know, K is 1, 2, 3, or whatever. And I'm going to multiply this times my standard deviation. But again, I don't want the standard deviation reference to be moving around when I copy my formula. So I'm going to do an absolute reference around that. Okay, so I'm going to press enter. And what I see here is that I can see, let me just look at that formula again. This is D2, which is the mean, minus K, which in this case is 1, times D4, which is the standard deviation. And if I copy this down just by clicking on this, then this one is going to be D2. Remember, I had the absolute references around the D2, so it didn't change. But the C8, this one came down to where my K is 2. And again, my standard deviation stayed the same. And I can see that this one's doing the same thing too. So I've got my lower numbers here that are, you know, 1 standard deviation below the mean, 2 standard deviations below the mean, 3 standard deviations below the mean. And I'm going to do the same thing here. Okay, so I want this to be the mean. I don't want that to move around. Plus K times the standard deviation. And I don't want the standard deviation reference to move around. So there are my upper ones. And I copy those down. So I know what I've got here is I've got an interval that is within 1 standard deviation of the mean, 2 standard deviations of the mean, and 3 standard deviations of the mean. And again, I'm going to go in here and just clean this up a little bit. I'm going to bring these down to maybe 2 decimal places. So think about what the empirical rule tells us. The empirical rule tells us that within 1 standard deviation of the mean, approximately 68% of the data should be there. Within 2 standard deviations, approximately 95% of the data should be there. And all or almost all of the data should be within 3 standard deviations. So we expect that about 68% of the data should be between these two numbers. Approximately 95% of the data should be between these two numbers. And all or almost all would be in here. Now, what we haven't really done here is we haven't really gone back and checked to see what the distribution looks like. We haven't checked to make sure that this thing actually has a bell-shaped distribution. But we could do that, and that would be using those methods that we talked about before, where we go in and we create the classes, and we create the bar chart or the histogram, and sort of check it that way. So I'm just asking you to trust me in this case. These things follow a normal distribution. They're bell-shaped. Okay, so now what I need to do is I need my frequency. And I need my relative frequency. Okay. So let me just clean all this up a little bit here. All right. Okay. And I'll just make this look a little bit better. Okay. So I need to do this. Now, of course, you could go and you could count out of those 40 measurements how many are between 97.55 and 98.78. But that would be sort of the hard way of doing this. We're learning some Excel skills here, so let's learn some commands. Now, these commands, sometimes these things get a little bit complicated. So let me just explain what I'm going to do here with this. I'm going to use a command called the Countifs command. And so equals Countifs. Okay. Now when I open this up, it's going to ask me for some different things. It's going to ask me for a criteria range and then the criteria. And then the Countifs command, which is different from the Countif command. With the Countif command, it just asks you that one time. But the Countifs command, you can do that over and over again. You can put in multiple criteria. So the criteria range here, that's just the data that we're looking at. Remember, we called that emissions. So I want to look at emissions. Okay. And what do I want it to be? I want to count that if it is greater than or equal to this number right here. Okay, so in Excel, I'm going to type in greater than or equal to, and I'm going to close that. Now, those have to be in quotes when you do that. And then I'm wanting it to look back at this cell right here. Now, whenever you have a number in here that comes from a formula, you have to tell Excel to sort of connect that to this this greater than or equal to that you did right here. And we do that using the ampersand sign. And so I want it to connect that to this cell. Okay, so Countifs. Emissions is the range we're looking at. I'm putting in, well, what is my condition here, which is greater than or equal to, and that has to be in quotations. And I'm connecting that to a cell, and you do that using the ampersand, and then you type in the reference of the cell, D7. Okay, so that was the first range, right? That was my criteria for that. But I also wanted to count that if it's less than or equal to what's in the cell next to that. We can't see it because this is covering it up. But you know, that would be E7 is what I want to think about there. I want it to be less than or equal to what's in E7. So I'm going to type in comma, and it's asking me for a criteria range. Well, that's still the same data set we were looking at before. And I want this to be less than or equal to, remember that's got to be in quotations. Use the ampersand sign. And now we want this to be less than or equal to what's in cell E7. So this command is counting my emissions that are greater than or equal to what's in D7, and it's counting what's less than or equal to E7. When I press enter right here, I can see here that I get 26. Okay. Now I've written this in such a way that I should be able to just copy this straight down. Because in this cell, what it's doing is looking back at D8 and E8. You can see that up here in the formula. And in this cell, it's looking at what's in D9 and E9. Now again, you could have done this by hand, or there may be other ways to go in there and count these things. But this is a way that works, and it's an Excel skill that comes in handy, you know, in all kinds of situations. Now let's remember that there were 40 measurements altogether. There were 40 measurements here altogether, and so the relative frequency is just going to be for this first interval up here, it's going to be 26 divided by 40. And I can copy this cell down too as well. This would be for the second interval, 0.925. This will be for the third interval down here. Now let's remember what the empirical rule should tell us, or what the empirical rule says these should be. The empirical rule says that this should be about 68%, and that this one should be about 95%, and this should be all or almost all. And we can see that this is pretty much following what the empirical rule predicts. And that's because the data set we were dealing with here was bell-shaped. If it wasn't bell-shaped, you can't use the empirical rule. But in this case, we see that this actually does conform to that pretty well.